Okay, hi everybody, I'm Kyle Provost from the STAT COE. We're centered at AFIT. So I want to share our paradigm for model validation levels. This is a fairly generalized validation paradigm. So it goes beyond just validating statistical models. Perhaps your model is a digital twin or some sort of AI system in a digital environment. And so we want a generalized paradigm to be able to evaluate all of them. A bit of a roadmap of where we're going to go here. First, I'm going to bring up a few statements about validation and digital engineering, and then we'll talk about what our paradigm is, and then I'll walk through a very simplified example of us applying this. I want to jump to the next page. Okay. So the importance of model validation, right? So validation, to get definitions out of the way, is a process that determines whether our model has sufficient fidelity for a specific intended use. So this is going beyond just matching up, does our model fit our data, but it's also saying, does our model also fit mission scope, for instance. This validation is critical to understand whether our models are useful, right? And there's an insistence that any sort of validation that we have needs to be based on rigorous principles. Sometimes in the DoD VC validation, that's a bit more ad hoc than we'd like, and it's decided on a case-by-case basis how we want to validate, and for any sort of enterprise level paradigm, that's problematic. Step forward. Okay, so what matters for validation? Well, first off, fidelity, of course, which is, I want to distinguish what we're talking about with fidelity, because in some cases we might be used to, especially in engineering, we might be used to thinking of fidelity as similar to complexity, whereas you might have like a physics model that has less parameters in it and you think it's lower fidelity. But we want to specifically talk about fidelity in terms of how well it matches reality, which is a bit more specific than just talking about complexity here. And then fidelity, we break down into some separate pieces that make up fidelity at large, including accuracy, repeatability, and resolution, which I'm sure we're familiar with these concepts. But beyond just matching up, how well does our model fit our data, we have other considerations. For instance, authority. How well do we trust our data, right? What are we comparing against? Our model can only be as valid as the data that we're using to understand our model. Finally, scope, as I alluded to earlier. So it's not enough just to look at, well, where does our model perform? You have to have the question of, okay, well, where do we have data? We might have some red areas where it's dangerous to test or cost prohibitive, or we may just have inability to get access to resources if it's adversarial systems, for instance, right? And so in terms of, we have to look at in terms of where is our data, where does our model perform, and where is our mission need? And the intersection of all of those is really the point where we're valid. Thank you. Okay. So we've talked about validation in digital engineering and how we need to assess it. So now I want to bring up what our paradigm is: model validation levels. So what are they? Well, first off, what do they need to provide? They are a measure for model developers to continuously validate systems, right? We don't want a one-off check mark, but models evolve just as systems evolve, just as the mission evolves. So we need a continuous paradigm to assess our models. Finally, as well as making improvements, it's a paradigm that helps decision makers understand the risks involved in the use of our models. This is more than just to give you, again, more than just a thumbs up or thumbs down, but understanding if we're going to use this anyway, what risks we have in that decision to do so. In order to provide these things, the MVLs need to, of course, be usable. Part of that means it needs to be, the theory needs to be at a point where the inputs are accessible to use a level with these. They need to be comprehensive, and that's just a statement that the pillars that we talked about on the previous page, it needs to address all those aspects of validation. And then, as stated before, it has to have mathematical rigor and consistency. Along those lines, it needs to be objective, applied the same way no matter who is building these model validation levels. Additional notes, they're automatable. This ties back to being usable. A lot of theory went into this, but ultimately we had a goal of keeping inputs very simple. So put in what your data is, put in what your scope is, and it will be objectively applied from there. And then, as well as ease of use, this also applies to that continuous improvement that we alluded to. Again, it's automatable. Then if you have requirements change, you have new data come in, if you have a mission change, it's easy recalculation of your validity. Now, final statement, these apply to predictive behavior models. Now, again, this is more general than just your statistical models. Anything that is, any sort of model that is giving you a prediction of what your system should be doing, model validation levels apply to. Forward. Okay. So that was how our MVLs work. Here's what the metric actually looks like. So ultimately, we want to validate against we want to validate our models against a supporting body of knowledge. That's more than just a single data set. We want to validate against our entire set of data sets that might inform us on how a system works. That goes beyond just your recent tests, but also any sort of historical information that should inform system performance or even SME judgment on how your system should be working. Ultimately, you know, some of your forms of information are more trusted than others. As stated before, you can only be as valid as your most trusted sort of data. So in this, we set weights, we set values to the data that we have, and then your model starts at the level of validity of your most trusted data source. From there, we'll look at the other pillars of validation, and we'll decrement from that to show how valid your data is, or not your model is, sorry. So as you can see from the table on the right, our MVL score is on a 1 to 9 scale. Ultimately, at the end, when you get your score, it'll be comparable to the way that we are rating the data types here. So for interpretability, if you had a score, say, of model validation level of, say, 7.5, you would understand that your model is about as trustworthy as prototype field test data or live system test data, or somewhere in the interim between those. And I already made statements about these last two, so I want to step forward. Here's our example. Again, a simplified example, we have a model of a toy catapult, right? And as a note, again, we're looking at how our assessment metric works, not how the system itself works. So there's problems with our model, and we intend for our paradigm to be able to show those problems for the sake of being able to diagnose and understanding the risks associated with our model. So what we've built is a Python model. It simply predicts what the distance of your projectile is going to be when you launch it, based on a number of input conditions for your catapult. It is a stochastic output, so there is variability in the results between different runs, and we do not consider any environmental factors in our model. Step forward. Okay. So we have a model, we have a system. How do we go about assessing how well our model fits the reality of our system? Well, first we need initial setups. So we've talked about scope. Initial setup largely considers your mission scope. This is where you define, where does my model need to work, right? So here you want to put boundaries, numerical boundaries on whatever your technical boundaries are, whatever your mission scope is. Again, same with environmental boundaries. And then we also need to define what our measures of performance are. What is it that's defining how well this model matches reality? In our catapult system, you can see from the picture here, our input conditions, the boundaries that we set are launch angles between 160 degrees and 180 degrees. Tension settings, that's how hard we're pulling the rubber band. Stop position, it's determined that we don't need to consider all possible stop conditions because a few of the stop conditions are not mission relevant. 5 and 6 shoot downward. And then for the sake of this validation, we consider no environmental changes. So this is largely valid over flat surfaces. Again, mission measure of performance is distance launched. Excuse me. Next step. Okay, so we've set up our mission scope, our validation area. What's next? Well, now we need to collect our data we're going to assess against. So as you stated before, we want to assess against the entire body of knowledge on a system. Here even though we collect all our data, again, we have a sort of weighting factor because even though you're looking at your entire body of knowledge, you know, if your model matches information from real world data collection or operational tests, matching that data is much more important than matching, you know, just your physics predictions or your SME judgment from earlier in program conception, right? And so that weighting scheme is used to help understand where matching is really important. In looking at this entire body of knowledge, we combine outputs with we combine our understanding, our body of knowledge with Bayesian methods. If anybody's familiar with some more complicated Bayesian methods, this would be power priors, using our weights as direct inputs into the power prior weights. For our specific system, this means that we have two reference to lean on. One is live system test, where we went out and actually fired these catapults. And then in those areas where we collected sparse amounts of data, we then also leaned on SME inputs for some teachers who have been using these catapults as DOE example tools. Step forward. Okay, we set up our space. We have collected our data. How do we actually go about calculating this? Well, first off, we need to look at fidelity. Now, fidelity it's not enough to just look at an overall sense of fidelity. There's some areas where your model may match reality. There's other areas where it will not. So you need to get a sense of fidelity across the entire mission scope, right? If you have that way, we can develop a full understanding of how our model works and how our system works, for that matter. And so to do this calculation, we directly compare our model output to our body of knowledge system performance. And we have our equation up here. Now this includes both a accuracy component and a variability component. And that's a crucial piece here to state that it includes both. A lot of times we validate with statistical models just looking at sort of accuracy. But again, if you have cases, you know, say we're using a missile, you can't just know a predicted point where it's going to hit. You need to understand that the schoolhouse 2 blocks away is not in danger, right? And so both components are necessary for a full picture of risk in applying a model. For our specific catapult example, we get an accuracy score of 0.55 and a variability of 0.54. Now these are on a 0 to 1 scale. Looking over here at our heat map, This is just showing the accuracy score, the accuracy calculations. It gives us an understanding of why. Here in sort of the central areas in our most normal operating conditions, we have very good fidelity. It would be easy to do some demonstrative tests and think that our model's spot on. But when we do a more comprehensive assessment, looking across the entire space, we see that edge cases become a problem. When we have extreme inputs from multiple of our conditions, our physics-built model fails, right? And so as you do the comprehensive assessment, we get a hard hit to fidelity because of those edge cases. There's a similar issue with variability. Now, that is, again, something that we expected to see here. Our model had an assumption of constant variance. That is a very, very poor assumption for our catapult, because when it's a short toss, there's not much variance. When you're going for maximum distance, there's very, very wide range of potential distances. So just as expected, our assessment properly found those issues and decremented our authority because of that. After we look at all aspects of fidelity across our entire space, we can then go to our next step. If you want to jump forward. Okay, we started at the level of authority of our data. We decremented for fidelity. Now we need to look at scope, right? Does our model actually fit the mission scope that we're needing to assess it over? Now this considers a few things. It considers both volume and density. This is sort of like extrapolation risk versus interpolation risk, right? So, we can look over here at our our data spread, 3D data spread over here at the right, and the red portion that you see is the actual extrapolation risk. So you can see that there's only a small piece with our actual model that we're missing. We have any given dimension, we match the entire spread, but there is a specific factor combination that's missing. And so that would be an extrapolation risk. You can see that as you go to our actual scoring, our volume coverage, 0.981 is the piece that's getting decremented because of that extrapolation risk, or that lack of volume. And we look at our density coverage, 0.998. Again, both these are on a 0 to 1 scale. And that's simply stating that if you look within the blue area, we have data thoroughly filling throughout. So both these scores are very good. We have a good data spread, we have good data density. We multiplicatively combine these scores to get an overall coverage. And then we again use that to decrement our authority. Stepping forward. Okay, so we've done we've looked at all the individual components of validity, validation. How do we combine this into an overall picture? So our resulting MVL is, again, calculated fidelity across the entire space. We look at overall coverage throughout our space, and we combine them. As we aggregate them, we then convert it back into a 1 to 9 scale instead of 0 to 1 scale, to get it on similar footing as what we started with, as we were looking at authority of data. So with our catapult example, again, we started at level 8 and decremented from there. We lost roughly a little bit more than 2 levels due to fidelity issues. Both our variability and our accuracy were lacking. Fortunately, we didn't lose a great deal to coverage issues. It gives us a resulting MVL of 5.74, and we'll talk about what that means on the next page. Okay, the maximum achievable score we could have gotten with this was 8. We got a score of 5.74. That would tell us that this model is comparable roughly to lab scale system test data in terms of how much we're going to trust it. Now we see significant losses here from fidelity, as we've already stated. what does this mean for us? Well, there's no single decision threshold here. This is sort of a quantification of risk, a quantification of trust, and it's ultimately for decision support. So this is where now the program manager or somebody higher up would need to make a decision. What decision might come out of this? Well, one, we may very well need to invest in model improvement, right? We saw significant fidelity issues. We may very well be able to improve our model to address those. Otherwise, we might downscope our model, right? We saw that it was performing very well in those central areas, in those normal operating conditions, and is failing in the edge cases. This might be a point where we'd say, okay, over this entire mission scope, we have poor validity. But if we redefine our mission scope to say we're only going to use this model for these sort of central areas, that may be a way to go forward with low risk in how we apply this. Finally, we may very well accept the low. Well, sorry, not finally. We may very well accept the low fidelity model. Just because it's lacking fidelity does not mean that was outside of our intentions, right? If the level of fidelity that we have is decided to be sufficient for the use case, we may decide that it's appropriate to go forward with what we have. And there's another case I haven't put up here that would be common, but doesn't apply as much to our catapult. And that would be, we may need to go collect more data. That's one significant risk. That's one significant factor in validating is if we are just missing information somewhere. If you're capable of gathering more, then that may be another area to invest. And this paradigm will show where you are lacking data and where there is room for improvement. Okay, if we can step forward. Thank you. Takeaways. MVLs are a comprehensive assessment tool. They give a comprehensive assessment of a model to provide a full picture of risk of model use across the entire mission scope. In addition to a picture of risk, they're a good diagnostic tool. They not only give you assessments, comprehensive assessment, but they give you information on where you're lacking, why you're lacking, so that model developers might have the resources to go back and correct in those areas. And then finally, again, this is automatable. And so once you have your initial inputs in, generally additional inputs are simpler still, and it will automatically adjust to any sort of new data inputs, new requirements, new mission scope. So good for a evolving picture of model validity. Any questions?
I have a couple of questions.
Okay.
So I'll just ask one right now. But oftentimes when we're looking at a model, we're receiving incomplete data from a variety of sources.
Yeah.
And often we use the model when live testing isn't possible. So if you downscope to the regions of high fidelity, then why don't you just live test? But really, how do you weight those data from different sources for your decision makers so that you make sure that you're using the model to the full extent while also understanding the risk?
So that's a great question, and it's sort of a multifaceted answer because it depends on where you have data and what data you have. So there's some cases where we have overlapping data in an area and lack of information in whatever your most valid is. And then there's other cases where we're sort of tiling over the space with different data sources. Again, like you have that red area where, hey, it's too dangerous, we can't test here, right?
Yes.
And so in the first case, the weighting is all baked into our Bayesian combinations. So it's weighting derived from that, from the chart that you saw. It's not actually 987, it's geometric weighting derived from that. It's a bit beyond this. As far as tiling over a different space, we we can't use Bayesian combination to combine, data that's here and data that's here. And so that gets, we still use a similar weighting scheme, but that ends up getting pulled into how we aggregate them together into a single picture. So you may very well, when you look at over the entire scope, you may very well see, we get a sort of pseudo MVL where you might say, oh, well, we're sort of level 5 over here and level 7 over here, and then we can aggregate to a complete picture where and there's some information lost in doing that, but there is this sort of understanding that if you are matching here with the high fidelity data, it does lend a sort of credence to you're more likely to be matching over here as well. So there is a little bit of a inherited authority across the space when you aggregate.
I would say only if you understand what your model output is across that space.
Yes.
And the variance of that.
And that's why we're doing these additional assessments like scope, right? If you don't understand your output across that space, that is largely tied to, generally, I'm going to say, interpolation risk, right? And so if you're lacking data within that range, then you're going to get, oh, sorry.
Yeah, so not the interpolation risk because you're not able to validate that data, but I'm just talking about understanding the model responses, the model output across the space. If you don't understand the model output across the space before you go into validation, then how are you allocating those resources and that weighting? I guess I'm concerned because in a lot of areas, all we've got is SME validation.
Yeah.
And in your schema, that is significantly underweighted.
Yeah.
And it may provide a completely different picture to the operational user of these models than the way, say, in specific use cases, they've used these models in the past. And so you're talking about a huge potential paradigm shift here.
So I'm not sure if I'm going to completely answer what you're trying to state here or what you're trying to ask here. But yeah, you may have an issue where you have live test here, you have SME information here. And so as we sort of go over that space, then we're saying, well, over in the area where we have live fire test, we're comparing directly to live fire test. Over here, we're only comparing to what the SMEs state, right? Yeah. And so we, again, you gain the space, they gain a little bit of validity from each other, but ultimately we have to keep that understanding in there of we're only informed by SME knowledge here. Now, SME knowledge is valuable. We're not throwing it away, but we do still need to appropriately decrement and with this understanding of we don't actually have the data to support this. Again, not all of this is necessarily going to be hard data like SME input. Oftentimes, if you're relying on a SME, I think oftentimes you do have other forms of information as well. Maybe not necessarily test information.
We don't progress.
Yes. So we have talked with some communities that had some concern about the sorts of information available to them as well, and I think the answer there is this isn't like a TRL or something where you have to hit a 9 to be able to go forward, right? Okay. This is a risk reflection. When we only have that sort of information, our risk is high, right? And so this needs to appropriately reflect that. That doesn't mean that we can't go forward. That means that in different sorts of communities, you might have different standards of what's acceptable. And a lot of that is reviewed in light of what information you have, right? I talk about how we have like a sort of starting point where we have this sort of information we decrement. If your information is only down here at a 3, but you decrement down to a 2.9, we're saying, hey, we've got high risk, but we very, very well match the information that we do have.
Okay,
Is that,
yeah, that's different than presenting a single number,
Yeah.
because I fear that that single number becomes like TRLs are used.
yeah, and we very much want to avoid that. We don't want to set incredibly hard thresholds. Part of this is trying to create something that can be simply communicated. The similarity to TRLs was an intentional choice at the beginning, but I think some people can get misled from that because the TRLs ultimately you need to get to the 9, right?
Or 5.
Depending on what milestone or what you're supporting and what,
But
yeah.
thank you for